Nitrous oxide injection. It is the easiest and cheapest way to make huge power at the touch of a button. You can adjust them from anywhere from a weenie like 50 or 75 horsepower increase all the way up to 500 and beyond. The question is, if you've got a late model V8 with this style of intake manifold, do you want to run a wet nitrous system or a dry nitrous system? Now I'm going to explain that, but first you need to understand how nitrous makes power. Nitrous oxide is injected into the engine. In the combustion process, the molecule of nitrous breaks up and brings a bunch of oxygen into the chamber. Then you can burn a whole lot more fuel because you've got the oxygen to support it. So either way, when you put nitrous in the engine, you've got to have fuel enrichment. The wet and dry systems do that two different ways. What they share is this plate right here behind the throttle body, and that's where you get all of this stuff shot into the engine. On the wet system, you've got both nitrous oxide and fuel. On the dry system, only nitrous is injected up here at the throttle body, and then the fuel enrichment is handled by the fuel injectors, which are down by the port in the factory location. And that requires some EFI tuning. So why would this decision between wet and dry be important if they're both enriching the nitrous oxide? Well, remember that these EFI intake manifolds are designed to flow dry air, not fuel. They have a much longer intake runner in them than you would see in a typical carbureted intake manifold, and they've got kind of a convoluted path to the port, and so fuel can fall out of suspension. And what happens is if you have a cylinder that is not getting fuel, it's gonna run really lean and potentially even break. It can burn spark plugs, it can melt pistons. If you've got a situation where you're only getting fuel into the cylinder and not nitrous oxide, that's gonna run really rich and can also lead to problems. So that's what we're gonna test here, wet and dry, to see how much of a problem wet can really be, and if dry also has a cylinder-to-cylinder distribution problem, and how to fix that, and if one can actually make more safe power than the other. Let's talk about the hardware that we're gonna use here. This engine is based on the super popular General Motors LS engine family. It's a 6-liter short block, but it's been stroked to 408 cubic inches. Up top, it's got rectangle port heads. They're a Blueprint engine's 259cc cylinder head. The compression on this thing is only 9.3 to 1, so it makes a little bit less power than you would expect from like an 11.5 to 1 LS. This makes about 550 horsepower with a hydraulic roller camshaft that specs out at 225 and 238 at 50 thousandths tappet lift. It's on a 113-degree lobe separation angle. It's got about 600 lift. The intake manifold that we're using is just a typical passenger car bone stock setup. .545 pound-feet of torque and 562.6 horsepower.
What we have here is our wet nitrous system. Steve is going to remove the throttle body, and this will be inserted between the throttle body and manifold. We'll have gasoline injected through this pipe, nitrous through here, and hopefully it'll distribute perfectly in this dry air manifold.
Nitrous is always so rewarding. We just made 653 pound-feet of torque and 646.5 horsepower. We're gonna compare our baseline to the nitrous hit. There you go. So we went from 563 to 646.80. The jetting usually nails it.
Yeah.
Yeah.
It's a bit rich for my taste, you know, and that's not too uncommon. I mean, it's probably more likely that manufacturers played a little bit safe.
For sure.
There's some tuning we could do here, particularly at this power level. This thing could run at NA power or air-fuel ratios.
We tuned a little bit. It went from a 26 jet, what did we put in there, a 22?
Yes.
Yeah, and it really didn't make that much difference in the air-fuel ratio.
4/10 or something. I mean, it went from 11.5 to 11.9, and I'd be okay with this, like I say, at 12.5 or something.
Right, but we're not going to chase every last air-fuel ratio, every last horsepower, because that's not what we're looking at here. What we're looking at is that cylinder-to-cylinder distribution, which looked pretty good.
Yeah, I'd like to see the graph, though.
Yeah. The next thing that we're going to look at is the air-fuel ratio for each cylinder in the engine to see if the intake manifold is doing good things or bad things with the 75 shot. And you're comparing it to naturally aspirated
Yeah,
here?
I'm just trying to get an idea of the spread more than really the number.
So the red lines are naturally aspirated and the black lines are with nitrous oxide. Remember that we had the NA tune-up leaner overall. That's why the red lines are above the black lines. What we're looking for is the grouping. And it looks like it's not as good as NA except for this one outlier.
Yeah, we've got an outlier, but look at this is a whole bunch closer here in general than all of this.
Yeah,
so I
it
think
is.
we're already starting to see some differences, and I think it's only going to get worse. But
And what that is the nitrous in the fuel, or more specifically, the fuel, not making it all the way there. Remember, this intake manifold is not designed to flow fuel.
No.
Yeah, and if you look at the design of it, what does it have, a big plenum and then a bunch of this going on?
yeah, it's got runners that to make that sort of runner length, it actually comes all the way across and around the top. So that's going to be really difficult to carry any sort of liquid, you know, and I think it might get to a point where it has trouble even carrying the nitrous if you were to get into bigger loads.
Like a 400 shot or something?
Yeah, it's just meant to flow air.
Yeah. Jets that were supposed to make 150 made more than that. A 168 jump. Our new power numbers are 730 horsepower and the torque, 787.
This is starting to look like a curve I enjoy.
Look how the power
flat.
curve just
This
comes
is a
in
pretty
flat.
decent tune-up when they're that flat and carry. That means the calibration is fairly close. Now you're starting to see that hard move like you're used to seeing.
Yep, for sure. Pretty good. How about the distribution?
Well, now that...
That's a different story. Tell me what you want to look at as far as
this is the one that
spread
I
there.
was getting a little nervous with. It was up at 13.
Yep.
And we're down at...
And those guys are 10 and a half.
Yeah.
That's a pretty good spread.
Yeah. And as going back and looking at the NA stuff, we remember up there it was grouped pretty decent except for that one outlier. Now we're starting to see where it's not able to carry well.
Yeah, 13 to 1 is where we're just beginning to get into scary on nitrous. You don't want it that lean. Ideally, you want it basically at the same air-fuel ratio that it runs best naturally aspirated, and maybe a tick richer if you really want to be careful.
I'm kind of wondering what the distribution looks like versus NA.
Go for it. It's NA's way better. That's the answer.
We have the
take a look.
technology.
Oh, yeah.
Yeah.
Wow.
Basically, this spread versus that spread.
Yeah.
So it's more ungood.
It's getting sloppier as we're adding more fuel in there.
The thing this really tells you is that you can't completely trust your oxygen sensor in one pipe because it's giving you an average and you're probably like, man, I'm right on. I'm 12 to 1 or whatever.
And you might have a cylinder at 16 that you don't even know about and blow your motor up.
Yep. So next step is we're going to the dry shot. Nitrous only in the manifold and enriching it with the fuel injectors. Here's the power numbers for our 150 horsepower dry system, 724.8 pound-feet of torque and 726 horsepower.